Okay, welcome to Analysis 1A lecture. Is this 8? I believe this is 8.
I don't know. I think so. Maybe.
I believe this is 8. Okay, guys, really fast. Today is, what's today? Wednesday?
Yep.
Limits test is Friday. And does everyone know what's on the limits test? Everyone got their quizzes back? I mean the quiz retakes back? So today was do a bunch of problems on derivatives, and also the homework was to finish the review packet. How is that review packet going?
It's alright.
Good. The answer key is more or less up on Edline now, so you should definitely check that. You should study for the test. The test is going to be Thursday. I think it's Sunday. Friday. What else? Is there anything else that we have to talk about regarding limits? I feel like there is. Wait, did we end class with this weird conversation about how, like, if one limit exists and the other one doesn't? No, that was 2 classes ago, right?
Yeah.
That was 2 classes ago. So what we are doing, what I wanted to do today was maybe spend like 5 to 10 minutes max going over the rest of the limits review packet. Should we do that, or just like not even? Harun says no. Are we good?
I mean,
I agree with Harun.
Okay, the one thing is, I think is, did you do the limits review packet?
I always do them the day before the test.
What?
That's the
Like
most terrible thing I ever heard.
I think it's a good thing.
It's a general argument for doing everything at the last minute. It's not. There's
No, not
whatever.
procrastination.
Don't talk back. This was new today. You didn't do it. Yeah.
Wait, can we just talk about like?
All right.
Wait, can
Wait.
we talk
We
about,
need what?
Like problems like number 5 and number 10. Can we just talk about like what?
Problems like number 5 and number 10.
It's like fresh in your mind. Yeah, I mean that's true. But like you also.
That doesn't make any sense. Yeah, we can do problems. We can do problems like number 5. Number 5 gives you some function, and the function is f of x equals a squared minus 2 when x is negative, and ax over tan x when x is positive, and says find all values of a such that the limit as x approaches 0. So find a such that the limit as x approaches 0 of this function exists. That's what it says, right? Is it right? Yeah, so find a such that the limit as x approaches 0 of this function exists. Well, in order for this limit to exist, the limit from the left must equal the limit from the right. Well, a is some constant, so the limit from the left of this function, the limit as x approaches 0 from the left of this function is just the limit as x approaches 0 from the left of a squared minus 2, because I followed this rule when I'm to the left. And thus, this is a squared minus 2. And the limit as x approaches 0 from the right of this function is the limit as x approaches 0 from the right. Well, now I'm on the right-hand side, so I follow the other rule. So what is the limit as x approaches 0 from the right? Is ax over tan x. Well, now it's just a limit to do. And I guess I can just factor the a just straight out of there. So this is the limit as x approaches 0 plus, or this is a times the limit as x approaches 0 plus of x over tan x. What's that? Secant x. What are you talking about? What?
Sin x over.
Yeah, do you guys just know this one? What is x over tan x? Yeah, this would just be a times. All right, so yeah, if we do what some of you seem to be saying is just split the trig up, right? So this is really just x. This is just cosine x cosine x over sine x, and that in turn can be broken up as a times the limit as x approaches 0 plus of cosine, which is just going to be 1 times the limit as x approaches 0 plus of, well, x over sine x is, I guess if I wanted to, I could write it like this, right? And this limit we know to be 1, and this limit is also 1, and thus the answer is a. This is what you guys basically did? So the limit as x approaches 0 from the left is a squared minus a. The limit as x approaches 0 from the right, I've just shown with way too much work, is a. And thus, the only way for this limit to exist is if a squared minus 2 equals a. So bless you. So a squared minus 2 has to be 0. So this is a minus 2a plus 1. Or, no, that. And so this will work if a is 2 or negative 1. Is that what you guys got? So you didn't do this at all? You, go in the hall. I'm not, you need to do your homework. Banishing you on the video. You need to do your homework. This packet was due, today's Wednesday. Most of it was due on Monday. You didn't do any of it?
I find it more helpful to do than
No, that's not how it works. That's not, I find it to be more helpful. If the homework is due Monday, the homework is due Monday. The homework was to do the first 5 pages of the packet. You're supposed to take your packet with you and work out in the hall. The five pages of a packet are due on Monday. You should have it done by Monday. That's the thing. How do you know we're not going to spend all class going over it and you're going to get no value out of that? That's what's going on right now, for example. All right. So, and then the rest of it was due today. The whole point is to do it beforehand, so if you have questions, then you have time to correct for that. All right, the one problem which I thought was kind of important was the last one from the review packet. You can go out in the hall and join him. You scribbled some stuff here, which is, okay. So it says find and justify all horizontal and vertical asymptotes of f of x equals root 2x squared plus 1 over 3x minus 5. Okay, so this is a very interesting function. This is a function which I could theoretically have just given you in pre-calc and asked you to graph it, and you might very well have been successful. But now that we're in calculus, we definitely have all the tools that we need to understand a function like this. So the directions for this are find all horizontal asymptotes, justify them using the formal definition of horizontal and vertical asymptote, and then we're going to make a graph of this thing too. So how do we do this? Someone just call out first off where we think there is a thing. Yeah.
We should just start out by seeing what happens as x goes to at x equals 5/3.
Yeah, at x equals 5/3, there appears to be some kind of infinite behavior, and so we need to investigate that. So what is the limit as x approaches 5/3?
Plus.
Yeah, it depends, right? It depends. So let's do them one at a time because I feel like we kind of have to. So let's take the limit as x approaches 5/3 from the right and see what we get. And then let's also, and this kind of very, very clear work is exactly what should be on your paper. What is the limit as x approaches 5/3 from the right of this function? What is the limit as x approaches 5/3 from the left of this function? And then we're going to see what we get. Okay, well, let's do it. If I plug in 5/3, what's the numerator? A number, yeah, I'll take that answer. It's going to be just some positive number. So it's exactly how I would do that. How about the denominator? What's it going to be?
small positive.
Yeah, that's right. If anything is a little bit more than 5/3 times 3 is a little bit more than 5 minus 5 is going to be a tiny positive. And so if I take some positive number over a tiny positive, that's going to infinity. Cool? Okay, that is already enough for me to conclude by the formal definition of vertical asymptote that if as I approach 5/3 from the right, this goes to infinity, so there is a vertical asymptote at x equals 5/3. Is everybody cool with this? Yes?
You only need one side.
You only need one to show that it's a vertical asymptote, yeah. But I'm going to do both sides because I want to know what happens. Even though I kind of already know this is smart, that's probably short. But if the limit is x approaches 5/3 from the left, this is again going to be some positive number. And then on the bottom now, a little bit less than 5/3 times 3 is a little bit less than 5 minus 5. It's going to be a tiny negative, so this is negative infinity. Yeah, yeah?
Yeah.
Okay, cool. What else?
Infinity.
Infinity, yeah. We want to take the limit as x approaches infinity of root 2x squared plus 1 over 3x minus 5. So what happens as x goes to infinity? Well, what does happen? Yeah, it just does. And if your teacher makes you show this, and he does, then we can divide the top and bottom by the highest power of x in the denominator because it's kind of like a rational function. And when we do that, since x is positive, I can put the 1 over x back in jail, and this becomes 2 plus 1 over x squared over, and now this is 3 minus 5 over x. And the advantage of that is that these are obviously going to 0, and so this is going to root 2 over 3. Cool? and by the definition of horizontal asymptote, since the limit of x goes to infinity is this number, there is then a horizontal asymptote of y equals root 2 over 3. And now we do negative infinity. What happens is we take the limit as x approaches negative infinity.
Same thing, but like negative.
Same thing, but negative. Why, Mateo?
Because x is negative.
Yeah, the one common sense way is just because common sense, right? Mateo says, look, if I plug in like some giant number, like, I don't know, negative 1,000, then this is going to be roughly, like just 1,000, right? Because the squaring and then taking the square root, or I guess roughly root 2 times 1,000. And then on the bottom, but now this is going to be negative, right? So it's not going to be the same answer. It's definitely a different answer. The way we can show this is to, again, divide the top and bottom by x. But now, since x is approaching negative infinity and x is negative, I write this as negative 1, or I guess it's the other one, right? It's negative 1 over negative root 1 over x squared over 1 over x. That's because when x is negative, this top evaluates to 1 over x. You understand what I'm talking about? We did this in class. Okay, so this because the limit as x approaches negative infinity of negative root 2 plus 1 over x squared all over 3 minus 5 over x. And this is going to 0, this is going to 0, and so what we get is negative root 2 over 3. And by that, we have a horizontal asymptote of y equals negative root 2 over 3. Okay, so this is kind of practice with limits, it's kind of practice with the formal definition of vertical and horizontal asymptote. In addition, I'd like you to graph this now. Can you tell me some other things about this function? What else? Yeah, Emma.
Because like,
yeah, Mateo said y-intercept, what is f of 0? It's just, is it negative a fifth?
Yeah.
Yeah, it's just negative a fifth, so that's like kind of a thing. Are there any roots?
No.
No. Roots, none. What else?
Sine chart.
Sine chart, that's actually a good idea. Sine chart, I guess it's just 5/3, right? The numerator is always positive, so it's just going to go negative positive. Alright, I feel I'm ready to graph this thing. Maybe.
Oh yeah, you can see.
Yeah, I'm going to get to that in about a second, Yob. But yeah, so root 2 over 3, root 2 is like 1.4, so that's about a half, I guess. So if that's 1, I have my one asymptote is here, and that's 1 something. There's another one, something. And negative a fifth is my y-intercept. And then at 5/3 something happens, right? So that'll be like here. Okay. So, good. I'm almost ready to go, I guess. But one question is, does this function cross the horizontal asymptote? So you guys try this? How do we do this? There's no obvious polynomial long division way. Instead, maybe some of you saw by checking the answer key, because you just did that. But if you haven't done that yet, do it right now. When does this function ever equal root 2 over 3? If you haven't done this yet, do it now. Did you do it already? No. Just do the algebra. It takes like 2 minutes. Did you do it yet? What's there mean? No, I want like a number. Yeah. Yeah, solve that equation.
Yeah. Who's that?
Which one?
Who's that kid?
What?
In the top right. Oh, the Asian kid? Yeah.
Oh, it's just some kid. It's just, go look at, no. Look at it later.
Okay.
It's just some weird, no, it's just some kid. It's just some kid wearing like a navy blazer and like a button-up shirt all the way to the top button doing a pull-up. It's just the most ridiculous photo I've ever seen in my entire life. So I cut it out and I wrote, I can do it. And it's an inspirational poster. That's neither here nor there. Did you guys already?
Yes.
Okay, good. So Sydney's killing time. Some of you did already. The rest of you are doing it right now. I will do it. So you get something kind. Oh wait, I'm screwed up. No, I didn't.
No, you didn't.
Yeah, no, you didn't.
Yeah. Yep. Really ugly fraction.
So did you get 41/60ths?
Yes.
Yeah. So it turns out that when x is 41/60ths, my algebra tells me that this function is either root 2 over 3 or negative root 2 over 3. I can't quite tell. Which is it?
Root 2.
Negative root 2 over 3 because this is 2/3 and my sign chart tells me that to the left of 5/3 I'm negative, right? So at roughly 2/3 I must be down here. And in fact that point is 41/60ths comma negative root 2 over 3.
Oh.
So putting this all together, this enables me to make a very accurate graph of this function. Let's see, it crosses there and by the way crosses nowhere else. So as x goes to negative infinity, I'm pretty close to this asymptote, and I must be just above it because I don't cross it. And I'm staying negative until 5/3, so I kind of go up and then, let's see, I must kind of hit here and then eventually go back down again without ever crossing because there are no roots.
Yeah.
Something good so far?
Yeah.
Yeah, and then eventually as x approaches a little, as I'm a little bit to the left of 5/3, I'm going down to negative infinity. So my calculations tell me, and more than 5/3, I'm up here at positive infinity, and then my end behavior is root 2 over 3, never crossing that asymptote either. So this is a pretty accurate graph of this function. Do you guys think you can handle a problem like this if it was on the test? Because there will be one good. All right. Good. Let's consider this review packet done. Those of you who haven't finished it yet, you need to do that ASAP. Let's go get Robbie Fleischman out of the hall, and let's move on back to derivatives. We have like an hour to talk about derivatives. That's not enough time. Wait, is this the class? Is this also where we never did this one thing? Oh man.
Did one thing.
Oh well, we'll do it now. Okay, first off, there's this theorem. So theorem. There's a theorem which says that differentiability implies continuity. Alright. And some of you may have seen this in the book on the section, in the book. And what this says, this expresses a kind of a common sense idea that basically if some function is differentiable at some point, so if f prime of a exists at some point, then f is continuous at x equals a. Okay. So if a function is differentiable somewhere, then it must be continuous there. Well, do you believe it?
Yes.
Sure.
The converse is not true, and I think this was the class where we didn't get this. So maybe we'll just do this now really quick. I'll give you a function. Here's a function. F of x equals absolute value x, and what I want is the derivative at 0. Go. Using the definition of the derivative. We never did this, right?
Yeah.
It was kind of a homework problem. Yeah, it was. And all the other classes I meant to do it in class, but I think we ran out of time. So you have two options, right? By the definition of the derivative, it's either the limit as x goes to 0 of f of x minus f of 0 over x minus 0. Or, if you do it the other way, the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. Right? You guys can draw the little pictures each time to help you remember that this is the correct definition. It turns out these both end up being the exact same thing, right? Yeah, so this is the limit as x goes to 0 of the absolute value of x minus the absolute value of 0, which is just 0, over x. So, what is this?
0 plus 0 minus.
Yeah, Busey says this limit does not exist. This is a classic limit that we have seen multiple times. Not existing, why? 10 reasons. I guess the simplest reason is to say, well, the limit from the left of absolute value of x over x is, by the definition of absolute value, since x is now negative, this is the limit as x goes to 0 minus of negative x over x, and that's negative 1. But the limit as x goes to 0 from the right of absolute value of x over x is, by the definition of absolute value, since x is a little bit bigger than 0, that numerator is positive, and so this is x over x, so it's just 1, right? So this limit does not exist, and we've seen this graph before also, right? Looks like this for cha. So this limit does not exist. And yeah, we didn't get to this last class, but the derivative is defined to be a limit. So if the derivative is defined to be a limit, if the derivative does not exist, then we just say, we're just forced to conclude f prime of 0 does not exist. You guys okay with that? Oh, and the other way sometimes we say f is not differentiable at x equals 0. And you're correct that you guys had some homework problems like this, where you had to do at least one where you had to do a derivative and it turned out it just didn't exist. All right. So derivative is a limit. A limit is a number, assuming the limit exists. If the limit doesn't exist, then the function just doesn't have a derivative. Comments? I feel like I have comments. What is this? Can someone tell me what does this mean? Yeah, you.
So if you say the derivative is the path an object would take if it kept going on the path it was taking, we can't really say what path the object would take if it was traveling on absolute value of x, because if we're going from the left, it would be going it would keep going down on the line y equals negative x. But if it was going from the right, it would keep going. It would go in the opposite direction on the y equals x graph.
Interesting. Okay. Yeah, that's kind of cool. I'm going to come back to what you said in a minute. Yeah, Laura.
Well, I don't know, but from a more geometric decision, I think that we're looking for the point that's tangent, right, to the curve. And I think there'd be a whole bunch of different points, lines that go through this point that would be tangent, and they would only go through one point in the graph, so you couldn't just find the slope of one line, because you could make a huge bunch of lines.
Yeah, it gets kind of weird, right? So Laura's saying, well, look, man, the derivative is supposed to be the slope of the tangent line to the curve. Well, what is the tangent line to this curve? There's one, and maybe there's kind of another one, right? It seems as if this curve has a bunch of tangent lines or something. Certainly something weird is going on there. That's one way of putting it. Anyone else? Another way. Emma.
The function just changes I guess the direction, the way it's changing instantaneously.
Yeah. So the derivative is supposed to be the slope of the tangent line to the curve. That's the sort of derivative as solution to a geometry problem. The derivative as solution to a physics problem is supposed to be the instantaneous rate at which the function is changing. So what's going on with this function? It's going along at what rate is this function changing?
It's all negative.
Yeah, a -1 rate or something like that, right? So it's this function is moving at 1 mile per hour backwards, and then later on it's moving at 1 mile per hour forwards. What's it doing at 0?
No,
It's yeah, you should be making weird I'm not sure kind of noises, right? Just something that's not actually possible to do, I guess, right? In the macroscopic world, which is to just instantaneously change from going -1 mile per hour to 1 mile per hour. What's happening, the question of what is the instantaneous speed at 0 is no answer or something like that. Then Eob said something which is to the extent that the tangent line is supposed to represent the path that the object would take if it kept doing what it had been doing. It's like it had been doing so totally different things on either side of that point that I have sort of like no information or something like that, right? Do you guys kind of feel like this just sort of all makes sense? You can analyze it from a physics perspective, from a geometry perspective, and then the one perspective that obviously we started with is just, dude, just a derivative is just a limit, so just do the limit. And if it turns out the limit doesn't exist, it just doesn't exist, and that's that. Okay, are we cool?
Yeah.
Okay, let's do another one. What is, take this function, the cube root function, what is f prime of 0? So something also kind of weird happens, right? Do you get cube root x over x?
Yeah.
Yeah, and what is that?
2/3.
Yeah, we could do some algebra 2 or whatever and write this as the limit is x to 0 of x. You said something, right? What? What? What's the cube root of x over x?
Negative
1 over x.
Yeah, this would be, I mean, yeah, this is 1 over x to the 2/3. Okay, I mean, this is just like, right? This is just like easy. This is like middle school exponent rule action. Cube root x is x to the 1/3, so you just subtract. So, okay, so what? What is 1 over x to 2/3? What does that mean?
Does not exist.
What does that look like? Graph that function, 1 over x to the 2/3. This should be like, this should take like 10 seconds for a magnet student. What is x to the 2/3? X to the 2/3 is bird. What's 1 over bird?
Other.
Volcano, yes.
Volcano, yeah.
1 over bird is volcano. X to the 2/3. What? Don't pretend you don't understand what I'm talking about. Bird. Plug in, you get 1, 1, negative 1, 1. If you plug in 8, you get 4. If you plug in negative 8, you also get 4.
I got the volcano.
It's bird.
I
What
got
X
volcano.
to the 2/3 is bird. And what's 1 over bird?
Volcano.
1 over bird is volcano, yeah. So it's volcano.
That's a
Terrible
really
marker.
skinny volcano.
Yeah, it's a little it should be less skinny. So anyway, what's the answer to this limit? Yeah, it's infinity, and in this case, I'm going to, it's my prerogative to say that this limit does not exist, because that's kind of what's crucial, right? A limit, yes, the limit is infinity, but more importantly for our purposes, the limit does not exist. A derivative is a number. A derivative is a limit, and a limit is a number, except when the limit doesn't exist. It just doesn't exist. So what can I say about f prime of 0? Exactly. Yes, unfortunately, f prime of 0, again, does not exist. This cube root function is not differentiable. What does it all mean? Alex Clark.
F is not differentiable as
Yeah, why? Why, though? Why?
Exactly. That's why.
No, but why doesn't the limit exist? Why is this function not differentiable at 0, the cube root function? Graph cube root on your paper. There's another thing that should take 5 seconds. You need to go really fast today. People at home, you need to watch this on 0.5 speed. I'll talk as fast as I possibly can. Root, can you raise my backboard?
Yep.
That's pretty cool.
Eob. We're going to go at Eob speed. Eob, what's cube root look like? Do it with your finger. Yeah, it's like the cube function, but sideways.
They have a name for this one too.
It's called the cube root function. That's what it's called. And it kind of, I exaggerated that a little bit too extreme, but it kind of gets super flat, right, towards the origin. Just like that, just like x cubed does, which is the inverse of that. So what's going on at 0? And you're just loosely in your own words, yeah, maybe Emma.
It goes straight.
It goes straight.
It goes further
Yeah,
than the
the
line.
tangent line is like everything's okay, and then suddenly, to the extent that the derivative is supposed to be the slope of the tangent line, we have like a vertical tangent, right, whose slope is infinity. That's like an algebra 1 classic. So this actually sort of makes sense in some ways, the slope is infinity, but the slope is undefined, so we say the derivative doesn't exist. Okay, and you can have all kinds of interesting and fascinating conversations. I recommend talking to Gabe about this as to whether you feel that this function has a tangent line, or it has an infinite number of tangent lines, or it has no tangent lines. This is like a borderline philosophical conversation. And over here, does this function have a tangent line, or does it have no, or does it not have one, or does it have one but it has undefined slope? All these things are very interesting and fascinating, which we're going to skip, and we'll talk about a logic math question. Good, we're skipping. Okay, so we see these examples of functions which are not differentiable. We have a theorem which says if a function is differentiable, however, it must be continuous. Does this seem reasonable?
Yes.
Yes, it does seem reasonable. We're going to prove it right now. And the other two classes are doing a terrible job of this. So I feel like, period, you guys just need to rock this. Ready?
Uh-oh.
Mateo, let's do it. It's a formal proof, so it's a little bit hard. But it's not hard because it's hard, it's just hard because it's technical. So that means, like, it's just, I wanted like a formal, using the definitions and everything like that. So explain, how do I prove a theorem such as this? Anyone? Yeah, Gail.
If if the differentiable, can you read that again? F prime A.
If f prime of a exists, then f is continuous
So
at x equals
you know
a.
that if prime of A exists, then the limit of F of A exists.
Wait, first we need to just say like one thing to make sure, don't think that this is beneath us to mention this fact. Yes, Mean?
The thingy exists then the, like,
Even before we get to that, we have like a logic issue to do with the Alara.
No, we just have to assume that f is differentiable.
Yeah, okay, some people think this is obvious, some people just goes over that completely, but yes, this is a conditional. And in order to prove a conditional, there's just a way to do this. To prove the conditional, we assume the antecedent and derive the consequence. So to keep the logical structure of our proof intact, just like let it be known that what we are going to do, and this word should appear somewhere in your paper, is that we're going to assume that f prime of a exists. And from that assumption, and that assumption only, we will conclude down here that f is continuous at x equals a. Okay, that's like the first thing. Sorry, now back to Yao, because you were actually talking math. This is just like logic.
Okay.
Math.
So if F prime of A exists,
Yeah, it
then
does.
we limit as F of A approaches A. Too many words.
Oh, words are hard. Yeah.
Just like, it might be good to like outline what